Thank you for inviting me for this talk. Wait a second. Got it. Yeah. I'm guessing there will be students in the audience, so I'm going to go a little slow. This is not a conference, so I want you to ask me questions and stop me anytime. Okay. So just if you can unmute your mic and just talk. Okay. So I'm going to talk about light and matter. It's an optical society, if I'm not wrong. So my goal will be to show you in terms of engineering these two-dimensional materials, devices from them, to make them more and more sensitive to light in terms of intensity, in terms of the spectral range, and so on. Okay. So to get started, two-dimensional materials is, I'm quite sure this is all of you know. These are materials which are intrinsically layered in the sense that you have the two subsequent layers are far more weakly bound than the atoms within the plane. This is started with graphene. You can see the typical interaction between two graphene layers is about 1,000 compared to a standard covalent bonded solid or ionic solids if you go away from the plane. And that is the reason why you can separate out individual layers and stabilize them on some substrates. Okay. I'm guessing there is no problem with my internet and you can hear me without any difficulty.
Yes, sir.
Right. Good. Okay. So if you look at, there are a large number of such materials in principle possible. You can see there's about 1,825 according to calculations. Of course, not all of them needs to be stable or environmentally, environmentally stable in particular, or on a surface. But in principle, there are a large number of materials which can be separated from the mother solid, and then individual layers can be extracted. And they are typically, when they appear typically in the solids, when the out-of-plane interaction, roughly the energy scale is about 20 milli-electron volt per square angstrom or below. You can see this carbon, that is graphene, boron nitride, chalcogenides like tungsten telluride, black phosphorus. There's a large number of such materials which are in principle possible. Okay. We now know about 30 or 40 of them, which can easily be separated on different substrates and exfoliated, including oxides. I'm not going to go in detail, but there's a significant amount of number of materials which can be exfoliated using a simple Scotch tape method, and then put it on a substrate. I'm going to come to the individual properties a little later, but let me quickly run through why this is such an interesting field that is becoming bigger and bigger every passing day. You see, many of these are semiconductors, and we have a very serious thrust on semiconductors of new types, because not only from the nanoelectronics point of view, where you are going into a regime of the silicon, where the silicon functionality is getting questioned because of short channel effect, because of CMOS configurations, bipolarity of the CMOS devices. And as many of those questions can actually be answered from a two-dimensional semiconductor viewpoint. So that is why IMEC and others have used graphene now as a two-dimensional material, like graphene, as logic devices in scaling up of the ITRS, or the International Roadmap for Semiconductor. The basic thing is 2D and graphene devices, where they can immediately get used. Why are they becoming so important? One is the gate scaling. You can now go down to extremely thin channel layers, which is really the atomic scale thickness, which is why you can make the channel length extremely small, and which is why, which is one of the big advantages over the silicon-based devices. This is called short channel effect. Because you can have bipolarity in the transport, you can integrate to CMOS, which is as back-end switches. We now have wafer scale manufacturing of this two-dimensional materials, graphene, transition metal dichalcogenides, which are going to be my major topic. So all these are in principle available at the wafer scale. These can lead to technologies which come with a clear disruption in terms of silicon. For example, you can make these neuromorphic devices. You can make these thermoelectric devices, which in far more difficult to just engineer silicon into those kind of structures. It's possible, but it's very energy extensive as well as complex. Of course, there are challenges like making large-scale devices, large-scale materials with appropriate, device-to-device control, the quality of these two-dimensional materials. These are ongoing challenges, but these are material challenges. Hopefully, that will be getting sorted out not too long in the future. As a result, you have got a large number of possible applications, right? Because of the two-dimensional devices and materials. Well, first example is electronics. As I told you, you can have niobium selenide-based family, twisted heterostructures as novel superconductors, which can be used in a multiple number of examples, for example, and volumeters for circuit quantum electrodynamics at very low temperatures. You have topological matter, magnetism. You can create magnetic two-dimensional systems like the chromium iodide family, and these are very new kids in the block, and they have created a huge amount of excitement. You have got now the entire class of quantum technologies. You can see there are 4 of them here. Communications, you can use the defects in two-dimensional materials as wonderful emitters. You can have sensors, which is what we are going to talk about today, where you can look at single photon detection using two-dimensional systems. The advantage of this, among many other advantages, is that they can operate at much higher temperature than the existing single photon detectors. And single photon detection is a key in any photonic applications, or not even photonic applications, even quantum electronic applications. You need to convert electricity and light interchangeably very often, and this is where getting single photon detection is extremely important. Quantum computations, graphene bolometers, and quantum sensing, where many of these defects on, say, boron nitride are spin defects, so they can be used for magnetic sensing. So there's a huge number of applications that is in principle possible with two-dimensional materials. We are going to talk about only a very small one, which is somewhere here. Right, so as far as two-dimensional materials are concerned, it will not be too wrong to say that this majority of the work are in the range of graphene and transition metal dichalcogenides because they are semiconductors. Of course, there are now magnetic 2D systems and others, but by and large. So if I look at the molybdenum disulfide, you can see this is how a typical electronic device on a molecular molybdenum disulfide look like. You have a single layer here, you put electrical contacts, then you measure the current between the electrical contacts as a function of gate voltage, which is acting as nothing but a field effect transistor. Typically, these are n-doped semiconductors, the molybdenum disulfide itself. And you see that as you make the gate voltage more and more positive, it is creating a high electron or high conductance of nearly on-off ratio of 6 or 7 orders of magnitude, even at room temperature. So this is, I'm going to skip. So why they are so interesting? Because of the sensitivity of these over nearly 15 orders of magnitude of voltage, of electromagnetic spectrum. You see, graphene is a zero bandgap semiconductor or semi-metal, which is why it can go all the way to microwave regime or a few megahertz, all the way to ultraviolet. You have got black phosphorus, which is a low bandgap, so you have got to infrared with that. If you look at boron nitride, which is from strategic applications to domestic applications in sensing as well as in detection of some form. Okay. So this is why we are interested in it. But there are some very neat physics in it. For example, why are the chalcogenides so interesting in terms of optoelectronic applications? Because their sensitivity to amount of light they can absorb to carry electricity. That's because if you look at their joint density of states, optical states, there's a very large peak, or called one of singularity, near the band, at the band edge of about 2.5 volts. This is the density of states. You can see that these guys have got a very large peak in the density of states, and as a result, they can easily absorb light. And a single mono layer or a molecular layer, a single molecular layer of molybdenum disulfide can absorb up to 5 to 6% of the optical radiation within the band gap of about, which is higher than the band gap of 2.5 electron volt, which is unthinkable as far as silicon is concerned, because silicon, the similar kind of absorption requires much thicker silicon piece. So that's one of the key advantages of using transition metal dichalcogenides in any kind of optoelectronic design. And when you look at light matter interaction at the interface or with 2D, this is one of the key considerations that we have to keep in mind. Okay, so with this, let me go through a little bit of basics and let's ask ourselves the question that what are the ways in which light and matter interact in most devices of solid-state systems, solid-state devices. One is called photoconduction, in which you've got two metals, and if you have a semiconductor in between, you apply a large electric field, and that bends the electronic bands. This is the conduction, and this is the valence band. And this is in the dark, and when I shine light on it, then you create a large number of electrons, jump out of the valence band, and then populate the conduction band. And because of the slope that you have created, or large number of electrons that you have created in the conduction band, you carry electricity, and that gives you the photoconduction mechanism. Okay. The second is photovoltaic mechanism. In photovoltaic mechanism, what you do, you create electron-hole pair, but then because of an inbuilt electric field, the electron-hole pair gets separated. This is one of the old examples of creating this built-in electric field by differential doping at the contacts. You can contact the palladium and titanium. This was a work from the IBM Yorktown group, in which, because of the work function difference between two metals, there is an inbuilt electric field. And now when I create electron-hole pair, because of this electric field, immediate electron-hole pair gets separated. And this is called a photovoltaic mechanism. In most cases, the photovoltaic and photoconduction mechanisms are somewhat difficult to isolate or to separate. But in certain engineered cases, you can, like this. Then you have got photothermoelectric mechanism, in which what happens is you have a system in which there are two different regions of very different thermoelectric coefficient, S1 and S2. In some cases, like in this paper, you have this by having one part as single layer graphene, other part as bilayer graphene. And because the electronic structure of single and bilayer graphene are very different, their thermoelectric coefficient is very different. So now what happens is that when you shine light at the interface or at the junction of the two different layers or two different regions, you create heat, you create an additional temperature difference, and then that temperature difference leads to different voltages across this two different thermoelectric coefficient regions. Okay, so that gives you a voltage difference between the source and drain. So this is called a photothermoelectric mechanism. And finally, the volumetric mechanism. The volumetric mechanism is nothing but you shine light, you hit the 2D material or any material for that matter. Volumeter means converting light into temperature, and the temperature change is reflected as a change in resistance or voltage. Okay, so these are major directions. What I'm going to show you that today probably the graphene and TMDC hybrids, or some of these 2D hybrids, require a completely different mechanism in order to explain their sensitivity to optical radiation. So before we go into that, let's have a quick understanding of what kind of metric that we should use. That's called the photocurrent is directly proportional to the photoexcitation power, the power of light that you apply, and the proportionality constant is called responsivity. It's essentially two different components: the internal quantum efficiency and the gain. The internal quantum efficiency is essentially how many from a given the number of photons, how many electrons you get. I think the number of electron hole pairs, the per photon that you create, is internal quantum efficiency. Okay. So each photon comes and strikes your system and it creates electron hole pairs. So internal quantum efficiency is the number of electron hole pairs you create for every photon. There's some additional terms because of the surface reflections, etc., but those I'm going to ignore from time. In addition to that, there's a gain. So the gain is something which is relatively non-trivial. So this is the number of charge carriers you create in the circuit for every electron hole pair that you have generated. So you see, quantum efficiency is the number of electron hole pairs per photon, and the gain is essentially the number of charge carriers per electron hole pair. So the total responsivity, or hence the photocurrent, is a product of these two parameters. So what is gain is very simple to understand. Suppose you have a PN junction diode, you shine light and you create an electron hole pair in the center. Okay, but because there's an electric field, say usually what happens when you shine light and you create electron hole pair, the hole remains localized usually, and then electron can move around. So the moment electron hole pairs are generated, electron rushes towards the positive end and vanishes into the battery, another one is generated. So basically what happens is, while before the electron and hole recombine like this, how many electrons you generate in the circuit is given by given by this gain G. So the trick here is to make sure that the electron and hole pairs do not recombine as long as possible, so that you can create large number of electrons in the circuit and hence large gain. Okay. What is the state of the art in terms of responsivity now? Typically, you can see there are a large number of two-dimensional materials. You can see it varies from over about 3 to 4 orders of magnitude. Graphene is very poor. Graphene is somewhere low. If you take a look at molybdenum disulfide here, it's also about 10 to the power minus 1 or 10 to the power minus 2 ampere per watt. So this is responsivity unit, ampere per watt. And although there are other organic lead halides, etc., they have shown somewhat higher responsivity, but they can also be because of intrinsic defects that one needs to keep into mind. But overall, if you look at the transition metal dichalcogenides, they are within about 1 ampere per watt or lower. Graphene is 10 to the power minus 6 or minus 4. Somewhere here. Okay. So one of the interesting directions that one took is the hybrid after this. As I said, to create a large gain, optoelectronic gain, you would like to keep the electron and hole pair away from each other so that they don't easily recombine. And this was originally suggested that, okay, why don't you keep this was a group from Spain, where they put some quantum dots. So what happens in the quantum dot and the graphene channel, and they put it on the graphene channel, when light comes and hits it, it creates an electron and it jumps and hole. Hole jumps out in this case, and it goes around the circuit many, many, many times. But because there is a physical separation between the quantum dot here and the graphene here, they don't easily recombine for a very long time. As a result, there was extremely high gain that was observed, and 10 to the power 8 per ampere per watt. And that essentially, led one possibility of designing the new type of photodetectors, or new type of interaction of light and matter using van der Waals interfaces. So that's what I'm going to do. Do you have any questions? So this is the basic idea of what we built. Okay. So what we will do today is to show that how we can create these van der Waals interfaces in order to create photodetectors with very large gain, and hence how do we engineer them for various applications and various functionalities. Okay. All that you need is a microscope here, and this microscope has got a special stage which are all home built. This is a stage with heater, and there is a stage here which can allow you to rotate the one layer with respect to the other for when we look at it through the microscope, so that you can create these van der Waals structures. The van der Waals structures themselves this is a common video that I always show. I'm sure so many of you have seen this already, but typically this is how we create the heterostructure. We use one layer to pick up the next one. This is a typical example, although this is one of the relevant examples today because we use this particular structure for single photon detection in van der Waals structures. This structure is a graphene on top. It has got a boron nitride underneath, and then a bilayer graphene and a chalcogenide layer at the bottom. So you can do whatever you want. Okay? There are at least, you can easily now make 5, 6, 7 junctions of layers in a van der Waals heterostructure. You know that one of the key reasons why van der Waals heterostructures were created was because if you put them inside, if you say put a layer of graphene between 2 layers of boron nitride, then you can increase the mobility of graphene very much. So you can see that this is a mobility of, near room temperature of graphene can be as much as 100,000 centimeters per volt second if you encapsulate it in boron nitride, 2 boron nitride layers. Whereas the black one is essentially a bare graphene sitting on silicon oxide, and because all the traps, etc., inside the silicon oxide, the mobility is seriously degraded. Okay. So this is what one of the earliest heterostructure that we made of simple a layer of graphene and boron and transition to dichalcogenide called essentially a molybdenum disulfide. It's very simple, as I showed you earlier. You pick up graphene and then you pick a layer of MOS2, put them on a surface, and then you put electrical contacts in such a way, and this is important, that you can measure the electrical transport through graphene while it is sitting on the molybdenum disulfide layer. So this is a typical example of a schematic of the system. You can see the molybdenum disulfide layer here with a graphene on top, and electrical contacts on graphene can measure the electrical voltage or current along the graphene layer while it's sitting on molybdenum disulfide. So this is what the key feature of such devices. You can see now that and there's a gate voltage. You apply a gate voltage at the doped silicon underneath. Silicon oxide here acts as a dielectric. So it's like a field effect transistor, but with an additional complication that we have a layer of molybdenum disulfide underneath the field. So you see that when your gate voltage is sufficiently negative, in dark, you have, this is the current through graphene, then you shine light, then the current drops from this value to this value. It depends on the gate voltage, but overall there's a drop in the current from some value to some lower value. So this is a negative photoconductivity. And the responsivity, as I showed you earlier, is essentially this is the photocurrent, which is why it's the difference between the dark current and the current in light is the photocurrent. And when I divide the photocurrent by the power of the light that we have shown on the structure, this number turns out to be enormously large, in the order of 10 to the power of 10 or so. So that is very, very exciting. It's nearly 10 orders of magnitude larger than the intrinsic photoresponsivity of most of the bulk semiconductors or even two-dimensional semiconductors like molybdenum disulfide. You see, this is how we used two very interesting features of these materials. So graphene is a material which has got high electrical mobility and very little light absorption. whereas molybdenum disulfide has a very little electrical mobility, but there's a very good light absorption. So by putting them together, we essentially created a new structure that can leverage on the good thing of both. Okay? So this essentially started the whole field of hybrid photodetection using van der Waals structures. So you can see in terms of the current state of the art, these kind of structures have got the highest responsibility known to us. Right, so what's the physics of it? The physics is simple. So this is an example which I would like to show with graphene and WSE2, which is another semiconducting heterostructure, another semiconducting transition metal dichalcogenide. You see that if I measure the photocurrent,
Arindam, I have a small question.
Please ask.
Yeah. So in the context of the optical properties, how important it is for the symmetry to be preserved in such devices? Meaning, if you are creating, let's say, a multi-layer structure, would it matter, let's say, if you have A, B, C in one order and you reverse that order? This is purely from an optical viewpoint I'm asking, because of course, surely there will be a difference in terms of electronic transport. But I'm just wondering what would be the effect due to the optical effect, if you can just.
So I can show you this. So if suppose A, B, C. So first of all, the optically active part are just two here in this case, graphene and the transition metal dichalcogenide. The two other parts in the cartoon, the video that I showed, and there are two other parts which are, say, for example, 2 layers of molybdenum boron nitride. They are essentially encapsulation layer. So they make sure that your device is not exposed to air. Okay. So now, but there are ways, and we are working on it now. There are in which we use more than 2 or 3 layers. Now, the question, if you ask it, how important it is to have, say, graphene at the bottom and say chalcogenide layer on the top.
Yes.
That's the question that you ask. Yeah. So it actually makes a difference. And that's a very important question because you see, if you look at this cartoon, you can see the molybdenum disulfide layer is here, sandwiched between the graphene layer and the gate down here. So now if I apply a gate voltage, you see, you create a band bending within the TMDC layer such that when I shine light and the electron hole pairs are generated, the electron has got nowhere to go but to go here. So you essentially use the electric field between graphene and electric field across the chalcogenide layer to drive the electron where you want it to go. However, if I did the opposite, that means if I did the graphene on the bottom and the chalcogen layer on the top, then you will not be able to create this electric field across the chalcogen layer. So even if you create the electron hole pair in the chalcogen layer by shining light, the electron hole pairs will preferentially get recombined within the chalcogen layer before they can actually get transferred into the graphene. So it's the sequence is important in most cases.
Thanks.
Nice, thanks. So you see, there's something important here. The important thing is, if you see the photoluminescence, the green or the blue one of the chalcogenide layer, which is WSE2 in this case, the photocurrent measured in the graphene essentially starts when, for all energies of the photon higher than the optical band gap, that is A exciton is where the optical band gap starts. Above that, you get a finite number of optical states. So you see that if the light is smaller than the optical band gap, there is no current. The graphene cannot see any current. The only current comes only when the optical excitation energy is larger than the optical band gap of the TMDC. Something which is going to come in soon, because we would like to extend the spectral range of operation of such devices. You can see this is the basic idea that when I create the electron hole pair, the electron jumps into graphene and it keeps on going many times. And this electric field that I just told you about allows you not to, or allows you to prevent the electron to jump back into the TMDC layer and recombine. So which is why the gain becomes humongous, and it can be easily about 10 orders of magnitude larger than any electronic, bulk electronic systems for optoelectronic applications. Right. So I told you in the beginning that this process is relatively a different process compared to known optoelectronic interactions, or light matter interactions in known systems. We had a photoconductive method, we have photovoltaic method, thermoelectric method, and volumetric method. But this cannot be categorized in any of those, because this is where electron, when it jumps out of the chalcogen layer and goes into graphene, it leaves a hole behind, and that hole essentially minutely positively charges the chalcogen layer as if it has got a gate. It acts as an additional gate on the graphene layer. So this is a mechanism which we call photogating mechanism, in which the process of light creates a charge layer, intermediate charge layer, which induces carriers in the transport layer, giving rise to the optoelectronic response. I'm not going to go into the detail here, but if you look at carefully at this graph, you see the markers here are the change in resistance of the graphene layer here, and this solid line is nothing but a derivative of the transfer characteristics of the graphene layer. What it simply means is that when the gating occurs, where the effect of gating is maximum, which is roughly somewhere here, where the resistance varies with gate voltage at the fastest, somewhere here and here, that's where the change in resistance that you get by shining light is maximum. And that's usually taken as a smoking gun signature of a photogating mechanism, in which the change in resistance is directly proportional to dr dVg, or the transfer characteristics or transconductance characteristics of the graphene channel. Okay, right. So there's a couple of more small interesting details because we are talking about optics. We are talking about electrons under, essentially going into electronic state of to the Fermi energy of graphene from an optical state. So in order to understand its temporal kinetics, how this goes as a function of time, you need to look at the rate equations. And one of the easy way to understand this is that suppose I shine light and you excite the electron from the valence band to the exciton state. And then the moment the electron is in the exciton state, it finds that it has got a lower energy configuration if it jumps out of the chalcogenide layer into the graphene layer, which is here, say at the Fermi energy. And this had been possible because of the alignment of the bands between graphene and molybdenum disulfide is such that it has this Fermi energy in between the ground state and the excited state of and the photoexcited state. So the electron finds it much easier to jump out of graphene and go into the Fermi level of the graphene, jump out of chalcogenide layer and go into the graphene layer. So the question that you ask, okay, then what is the rate at which it's going to happen? It obviously depends upon how many states are available here and how many electrons are coming back. So it's always a back transfer rate. So this is essentially a full rate equation in which the accumulation rate of electrons in graphene is given by the number of states available in the graphene layer. And if you look at the final output of this time scale tau will eventually determine how fast you are going to transfer the electrons into graphene. It essentially depends on two parameters, tau r or tr, which is called the transferring charge, the time it takes for the electron to go from the chalcogen layer to graphene layer. That time is in the order of 10 power of -14 -13 seconds. Tau r, which is the recombination time of this exciton. So before it jumps out of this and goes into this, if it recombines here, so then that's the time scale of an exciton, or the lifetime of an exciton. That's in the order of 10 power of -13 -12. And capital N is the maximum number of charge that can be transferred, and photon flux, that is proportional to the power of photons, is given by phi. Now, if I plug in all these numbers, it actually comes out to be in the order of 0.1 to 100 seconds. So if you shine light on this, the time it takes to reach its final current value or the resistance value is actually very, very long, even though the charge transfer time scale from here to here is just about few picoseconds or a fraction of picoseconds. It comes to about 0.1 to 100 seconds. Okay, so this is something we have established experimentally. You can see that it's so also it is inversely proportional to the power. So if the power is low, the time taken to reach the final state will be much longer. So that's exactly what you see. You can see this is a purely exponential relaxation. When you shine light on these structures, the lower the power, so the higher power is 7 femtowatt per micron square, it immediately goes. And then you reduce the power every time, and you actually see that exponential relaxation with longer time scales of reaching the final state. Okay, so this is an evidence also that in addition to electrons jumping out of chalcogen layer to graphene layer, quite a number of electrons actually comes back and through phonon assisted transfer, and that is why there's a dynamic balance that needs to be created, and that happens over a very long time scale. Okay, so we understand these interfaces quite well now, I think. So there are a lot of these devices that have been made, and this still continues to be a very active field. But I'm going to go in a different direction. I'm going to go to photon counting, and I ask because this is one of the major applications. If you are claiming that you have got a system in which you can measure light at an extremely high sensitivity or with a photoresponsivity in the order of 10 orders of magnitude, then naturally the question is, can you use them for counting electrons or photons? Okay, how many photons your system has received? And the implications are obvious. The implications are immediately in quantum technologies and various forms of extreme sensing devices. Now, if you want to ask the question about photon counting, first you have to ask, okay, what is the signal to noise ratio in such in such structures? Typically, if you look at in an optical element, the signal to noise ratio is given by this equation, where this n is the mean number of photons. F is an excess gain noise. So you see, gain is something which I have stressed from the beginning. I'll tell you where the gain noise comes from. And the sigma q is the noise in the channel, the electronics. You have graphene here. If you don't have graphene, if you've got APD, the avalanche photodiodes, etc., so that the electric current has to go through those devices. So that there's always a noise in the channel of the electronics. So usually what happens is that if this is signal to noise ratio, that means now assume that the gain noise is just 1. So if you don't have gain noise, F is 1 and sigma q is 0. In which case, signal to noise ratio is directly proportional to n, which is the mean photon number. And that's an ideal situation, that your signal is the photon number that is coming on your device. But that's not the case. It differs from that. Okay. Now, how? So this is a typical single photon detection of an avalanche photodiode. And if you look at where the noise comes from in such devices, it's primarily the gain noise that determines the functionality. For example, if you look at the way these avalanche photodiodes work, you bias them and the current essentially goes from one side to the other. In the process, the electron goes from one side to the other and it recombines randomly in a very stochastic manner with the hole. And this is essentially limiting. I told you in the beginning that the gain is given by the lifetime, and the lifetime becomes a stochastic quantity because the recombination of the electron and holes in this region becomes a stochastic quantity. And that is the origin of gain noise, which limits the performance of the avalanche photodiodes that we have in our laboratories. But look at this graphene MO structure. Here, the situation is very different. So this is the absorber layer of the molybdenum disulfide layer, and this is the layer of graphene. When I shine light on this, the electrons essentially are always moving in a region where there is no hole because it is moving in a pristine graphene channel. The electron and hole are created where the hole is physically separated in a physically separated region which is the molybdenum disulfide or transition metal dichalcogenic layer, and the electron essentially goes without any stochastic recombination with the holes for a very, very long time. So as a result, these kind of devices, the gain noise is essentially completely suppressed. Noise that actually determines the performance of these photon counters are actually the second term, which is the sigma Q term, which is the noise in channel, which is the graphene channel, simply because graphene channel is sensitive to local electrostatic potential fluctuations disorder and so on and so forth. So one of our major direction had been to understand how this leads to a performance in photon counting. So this is the noise equivalent power is given by under root of total noise, which is a short noise, which is 2EI dark, and the thermal noise. And because the responsivity, which is very large in our case, our theoretical noise equivalent power is 10 to the power of minus 21 watt. Okay, so look at the existing number of this, different optical elements that we have. We have silicon and in-gas based avalanche photodetectors typically have minus 15, minus 16. Quantum dot based systems like indium arsenide can be 10 to the minus 17, whereas superconducting nanowires, which are used in today's single photon detections in quantum technologies, is in the order of 10 to the power of minus 19. These guys are, 2 orders of magnitude even below that theoretically. Experimentally, that is not the case. Okay, so if I actually want to do a single photon detection or ask the question, what is the limiting number of photons you can detect using these structures? You can see a very nice experiment that was done. We did this by sending pulses. Okay, this pulse is essentially the maximum power, and the delta T is the width of the pulse. And we can predefine the pulse height so that we now know how many photons are being hurled at the sample. And then we essentially, from this pulse duration and height, we have the photon count, expected photon count, and this is the photocurrent we generate. So you can see the problem is that sensitivity is not 1 or below, it's actually a few hundred photons. So if you take these pristine devices, we still cannot go to single photon device counting, but our limitation is about a few hundred photons. Now, why is that so? The reason behind that is the noise is coming primarily in this one-shot measurements. The noise is coming primarily from 1 over F noise. So effective noise equivalent power is given by, in addition to the shot noise and thermal noise, the 1 over F noise, and we have measured the 1 over F noise in our devices, which leads to typical NEP of 10 to the power minus 17, which is about 100 photons. So roughly what we see in our experiment. By the way, how much time do I have? 5, 6 minutes, maybe 10 minutes? How much time do I have?
Sir, you can continue. It's a 1 hour talk, but you can continue.
Fine. Okay, just stop me whenever. If you tell me to talk, I keep on talking. Okay. So we actually, measured this noise from, when we saw this, we decided that, okay, we need to reduce noise.
Professor, can I ask you one question? That is very good. Yeah.
Yeah.
So, previous one, you were saying that the electron that the graphene channel is getting, it's coming from the MOS2 because the MOS2 is absorbing the light. Now, when the electron is coming to graphene, I mean, it can recombine in MOS2 itself, and that can generate some noise, isn't it?
Yeah, right. Very good. So what I was trying to say, that's precisely the mechanism we are able to suppress. Absolutely right. That if the electron can jump back into MOS2 and then essentially has recombined with the hole which is there, then you will create you can create noise. But those time scales are far faster. Once you reach the steady state of the operation of these devices, then there is no stochastic behavior at the time scales of these experiments. So you can see this in seconds, right? So the seconds money, it's in about 10, 12 orders of magnitude slower than the recombination time scale that is happening of electrons jumping out of graphene into the molybdenum disulfide layer.
Okay.
Arindam, Ashish here.
Yeah.
I have a follow-up question to this.
Sure, please.
So, I mean, when you shine light on this, so you create exciton or you create electron hole pairs initially?
We believe we create exciton, Ashish, because we create exciton simply because our layers are completely, it depends seriously directly on the exciton A mode, that is and then we have looked at trions also in, like yourself, but so far from the energy scale of our photoresponse, we believe it is the exciton that are important and not just electron hole pair. And there has been work which actually shows that the exciton is an unstable state when there is an additional layer of graphene next to the chalcogen.
I see. So this is what I was wondering, like, because these excitons normally are known to have very large binding energies. So that would mean that the radiative recombination times would be very, very small, very, very short.
Right.
So they are found to be of the order of like hundreds of femtoseconds and so on.
Correct.
So wouldn't that affect the photoresponsivity in a negative way? Because, this will take out all the responsivity within the MOS2 layer and would not let it go to the graphene.
Right. Great question. So Ashish, there had been a lot of work and a lot of interesting the work on pump probe. So it turns out that the electron transfer time scale from the chalcogen layer to the graphene layer is shorter than the exciton lifetime in the chalcogen.
That would be, you mean, some femtoseconds?
Tens of femtoseconds.
Oh, wow.
Tens of femtoseconds.
That explains it.
And this has been shown in pump probe spectroscopy as well as from calculations. Although I'm not particularly confident of the calculations, it's still not very clear about why the temperature timescales are so short. But it is true that the time, at least the pump probe spectroscopy shows that the transfer timescales are in the order of few tens of 200 femtoseconds, which is about an order of magnitude or a little bit more than that shorter than the exciton recombination.
Wouldn't it require to have like very, very large out of plane mobilities within MOS2?
Usually out of plane mobilities in most two-dimensional materials are not very high. Simply
exactly. So why is this very short times?
Okay. So I don't know whether other people know, but what I could get from some of the papers is that there could be some coherent effect because of the out-of-plane dipoles that gets generated when there is a charge transfer that happens from one layer from chalcogen layer to the graphene layer. So the moment that happens, there is an additional dipolar fluctuations, which leads to an off-diagonal components in the Hamiltonian between the graphene and the MOS2 that can cause some coherent effects. And this needs to be explained by a coherent effect. Just by simple incoherent effects, I don't think you can explain. There's such a short time scale.
Yeah.
Right. So I don't know, to be honest. I have to take my hands up here. But there are papers. There are papers which are saying that there could be some new coherent effects which allows charge to be transferred so fast.
Thanks, Arindam.
Yeah. Okay. So I go right there. I'll quickly say a few more things and then I'll wrap up. Okay. So I'll just tell you from device perspective, what have we done? We knew that the noise, 1 over F noise needs to be reduced. And there are several strategies. One of our earlier work was to make noise go down by making sure to reduce the contact noise. So this is an electronic thing because you see, at the end of the day, we are looking at optoelectronic devices. So we need to improve the electrical characteristics as well to have the best of optoelectronic functionality. So what happens is that you have we found that if the charge transport in the graphene layer interferes with the voltage leads or the current leads, it leads to noise. Partial reason behind it is that there's a damage that takes place when you deposit metals on these two-dimensional materials, and that leads to degradation of mobility electronic structure that leads to a lot of noise. And that we circumvented by creating this hallmark type of junction. So now what we have is that this graphene, which is now have these arms like this, and the voltage is being measured here. The current moves without any impedance across the samples. So the current flow does not look at or encounter any of the metallic leads. And we found that that way you can reduce the noise by nearly 2 orders of magnitude. So then we decided, okay, now it's good time to make a new device in which this is a device. Now we have encapsulated the whole thing, boron nitride and graphene, graphene and molybdenum disulfide layer between two layers of boron nitride. So you completely shield it from the environment, and then we put them in a make a hall bar out of it. Okay. Oops, I'm sorry. Can you see the screen?
Yes, sir, we can see.
Okay, good. So when you do that, now we have this extremely low noise system now, and we are doing experiments and seeing whether we can create nice optoelectronic elements. This is how we are moving as a device, moving the device front for such graphene ammonia structures. What we did though, in order to reduce the noise further, we used bilayer graphene. So this is the architecture. So graphene on top acts as a gate as well as a transparent electrode. Then there's a layer of boron nitride, and then there's a bilayer graphene, and then there is molybdenum disulfide, which is partnering the bilayer graphene. Why did we use that? There's something interesting. Bilayer graphene is a semiconductor which is parabolic bandgap. And if I apply electric field across the bilayer graphene, I open a band gap in bilayer graphene, and that leads to a reduction in the dark current by orders of magnitude. Okay. So now what happens is, if I apply electric field between this graphene layer on top and the doped silicon layer at the bottom, then I open a band gap in bilayer graphene, and now I shine light. Electron jumps out of through molybdenum disulfide, reaches here, but there is no dark current. So this is how we reduce the dark current significantly. And this is a typical device structure. This was a nice device. We made it not a while ago, 4 years ago now, 3 years ago. That acts as a beautiful gate on top, and then and a transparent gate. HBN layer doesn't absorb visible light, and our channel now is no longer single layer graphene but a bilayer graphene sitting on molybdenum disulfide. Okay, so you can, with this we could reduce the dark current. I mean, ignore the other lines. If we could reduce the dark current to nearly 5 nanoampere, whereas the conventional graphene molybdenum disulfide layers, the dark current is in the order of microampere. So at least 3 to 4 orders of magnitude reduction in the dark current could be achieved. With this, we were able to see single photon counting, even in noise single shot measurements. How? You can see that this is an overall architecture of the device. This is the bilayer graphene, and this is the molybdenum disulfide layer. And the whole thing is embedded between 2 gates, one on the graphene and one at the bottom. There's this large electric field between these, and that electric field has opened a band gap in the bilayer graphene, reducing the dark current. And then I shine light and I look at the, every pulse, how the electrical current in the bilayer graphene changes as a function of this electrical pulse. So you can see the electrical current in nanoampere, as I showed you, 10 nanoampere or so. With light pulses, in many of the light pulses, there's nothing, but in some of the light pulses, there is this drops that is happening. These are a series of light pulses. Okay, this is a train of light pulses. And now from this change in the light pulse current, I have normalized it with what is expected for a single electron or a single photon. So that can be easily estimated from the capacitive coupling between the graphene and the gate. So we can normalize the number of photons that are responsible for this change in current. So when I take this change in current and I create a histogram of such changes, then you see beautiful single photon detection. You see that the x-axis is the number of the change in current divided by that expected for a single electron or photon, and you can see this peaks at integer values, because when you shine pulses, there is never a single electron or a single photon pulse. There's an average number of photons in a bulk pulse, and that is Poissonian distributed. So these pink lines are essentially Poisson distribution with mean value determined by the power that you have used in shining. Okay. So we can, in principle, make a single photon detection using graphene noise and graphene and PMBC heterostructures. We are now looking at it better. When we published this paper, the referee said, this is nice, but this will never be used, which is something that we hope that we can prove the referee wrong someday. Right, so I'll give you another example, then I'm going to stop. How to extend the spectral range beyond that of the optical band gap of the light absorbing layer. Now, this is something which is going to come up soon. It should be 2022 because it hasn't been published yet. So suppose now what we did is we took a very interesting strategy. We know that when you shine light of the visible or the light which larger value of than the light with energy that is larger than the optical band gap, I transfer electrons from the chalcogen layer into the graphene layer. And those electrons stay there, right? Because most of them are stuck because they cannot come back, and it has changed the electrical conductivity of graphene. We decided, okay, is there a way we can sensitize this structure to the infrared radiation by shining a light which will take those electrons out and give them sufficient energy to come back to the chalcogen layer, and there it combines with the holes there, and then hence we can actually look at a recovery of the graphene of the current or of the dark current using infrared radiation. Turns out that was possible. You can see this is a train of light pulses. You can see that first light is 630 nanometer, which is the LED 1, and we have created a beam splitter and then essentially had two lights simultaneously and sequentially shining. So with this light, the current drops and stays there, because then even if you switch the light off, there's a strong persistence because many of the electrons are still stuck in graphene. They cannot come back because there's a large electric field preventing them from coming back into graphene, into the chalcogen. But then what I do after a little while, I shine another light using this second LED, and that is a much lower than the graphene, than the chalcogen band gap. But now you see that the electrons from the graphene layer jumps back into the chalcogen layer, and hence we recover most of the light that most of the, the dark current condition. So that makes this whole system now sensitive to the infrared radiation, which is much lower energy photons than the chalcogen band. You can, this is essentially what is given, and you can do this for many, many, many times, and you can create a beautiful detector of memory, whatever you call it, of infrared. We are excited because we can now sensitize graphene chalcogen heterostructures with extremely high responsivity to infrared radiation in the communications, so which is what is very interesting for us. Okay, so this is where we are with this. This was an old work with plasmonic work. Okay, can I stop now, or do you want me to continue for 2 more minutes?
So you can continue if you want.
Okay, 2 minutes then. I just showed this work with Kamlesh because there are people here who are leaders in plasmonics and similar quantum optics. So I just thought I'll show you this work. This is a very beautiful structure where these are all created by Amrish and his student. So essentially what happens is that silver nanoparticles were used in a dimer fashion and put in, and the graphene layer was arrested between two silver dimers, between two silver nanoparticles. Typically, the silver nanoparticles are 50 to 60 nanometer. And then the whole goal was essentially to see if the plasmonic surface plasma or the resonances can create a large electric field at the graphene. And this is really the ultimate large electric field, because graphene is, you can think of 2 nanoparticles are separated by the smallest distance possible, which is the graphene thickness. And that can lead to a very large optoelectronic plasmonic activity. Turns out this is the typical structure that Ambrish could create using the glancing angle deposition. First, you can take this beads, polystyrene beads, then you create this single nanoparticles, then you transfer a single layer graphene on it, and then you use a second glancing angle deposition, and then anneal it to create this exactly the on-site beads like this. Okay, so this is how the samples were created, and we could get an extremely large photocurrent of nearly 3 orders of magnitude in the plasmonic sensitization. Okay, that's more or less it. I'm going to not say anything about this at all. I'm going to jump, and I just want to finish it by looking at what is the state of the art. So this is not in press. This has now been accepted. So this is now in print. So basically, if you look at the overall individual two-dimensional systems, and this is the responsivity, and this x-axis is the bandwidth. That is how fast your detector works. Now you can see the responsivity is high in many of these single individual ones, but they are very slow. Usually they're about working, their typical bandwidth is in the order of 200 to few tens of kilohertz. Graphene is a very different guy because of its high mobility, and you can see the extremely large bandwidth, but the responsivity is very, very poor. Somewhere here. Now the question is the non-graphene hybrids, which are essentially the not using graphene as a hybrid, but for example, the chalcogenide and the topological insulant, bismuth chalcogenide. This is transition metal dichalcogenide. This is bismuth chalcogenide, and there are various other hybrids available. They're not very different in terms. I don't think there is a clear advantage of optoelectronic applications from these various structures. Okay. However, graphene has, if you partner graphene with many of these, you can see there is a clear change in the overall optoelectronic activity. There's a very large photoresponsivity when you create graphene as a partner. And I told you why. Simply because graphene can conduct electricity very fast. As a result, the gain, that is the number of electrical charge that you can create in graphene while you are waiting for the electron hole to recombine, is very, very large. And that graphene's mobility plays a key role in that. In principle, they are slow at this stage, but it seems that there are certain numbers which are the gain bandwidth product can be significantly improved by suitable engineering. And this is something which we are working on at this point of time as well. For example, can you use this instead of photovoltaic or photogating mode? Instead of charge transfer, can we look at the energy transfer to look at the speed of such photodetectors? So that's one of the directions that we're going. That's more or less it. I'm going to, this is overall structure. I don't want to repeat what I just said. Right, so I'm going to stop here. Okay. Thank you for your attention.
Hello, sir, I have a doubt. May I?
Sure, please.
So it was a great talk, but like I have a small doubt. So can you go to the graph where you have shown the first negative photoconductance while pulsing?
Negative photoconductance, say again?
Yeah, while pulsing.
While pulsing?
Yeah, first one.
Okay, I'm just checking where it must be some. Is that the one? So this is also negative photoconductance while pulsing.
So yeah. Why does it means I got it like when you send a pulse in, a lot of charge carriers are generated, which is transferred onto graphene, and so it means there is some. It might be recombining, let's say, with the holes and reducing the total charge. That's what's happening. At the same time, it's gaining slightly, decreasing the total conductivity.
Absolutely correct.
Now, why is there a very sharp rise again? I'm a bit confused about that part. Means when
Oh,
you
I mean to say here, why is this? Oh, okay, very good point. Sorry, I didn't say that, but you're absolutely correct. So what happens is that when you shine light here, it goes into the electrons jump out of the chalcogen layer and goes into the graphene layer, and the graphene was initially hole-doped, which is why when you transfer light electrons there, the effective carrier density decreases, and that is why there is a current through graphene decreases, and that is why it's a negative photoconductance, right? Very good. But then I switch the lights off, and because the charge carriers are trapped in graphene, they cannot come back. What I do in order to make them come back and recover my dark state is that I do a gate voltage pulsing here, which I have not indicated. I'm sorry about it. But what you do, you send a pulse to the gate voltage underneath, so that now the charge is allowed, the electric field goes down, and the charge is allowed to come back from graphene back into the chalcogen layer, and we recover the old dark state condition, so that I can now apply the second pulse, and this is how the cycle goes on. Is that okay?
Yes, sir. Now it's clear. Thanks a lot, sir.
Can I ask something?
Sure. Please go ahead.
Hi. So as
Hi,
usual,
Johan.
yeah, nice talk and very informative. So regarding again this MOS to graphene thing, so you have one layer of MOS2.
Yeah.
Graphene.
Well, it can be multi-layer as well, but not too many.
Yeah. So when you have very few layer, does not it mean that most of the light will pass through it and very few, means exciton per incident light will be less?
Right. So that's a great question. Ashwan, this is what I started with. See, one of the big advantage of these transition metal dichalcogen is extremely strong absorption. One of the key thing is that we could get, using 4 to 5 layers, our efficiency was, internal quantum efficiency was nearly 30%. Okay, that essentially means that, well, I mean, 4 to 5 layers, I think it was about 25%. Okay, 30% was thicker one. 20-25%. The reason behind it is the very large, van of singularity at the band edge, which leads to a very strong absorption. This is a key property of the transition metal dichalcogens. Okay, and that helps us in getting a large absorption and hence large efficiency even at a thickness of 4 to 5 layers, maybe 5 to 6 layers.
Okay. So another in the same system, like when you have, for example, 1 to few layer of MOS2, and you measure the exciton binding energy, pristine MOS, versus
Correct.
when you have graphene on top of it, do you see any change in excitonic binding energy?
Difficult to say. So look, I mean, so there had been work done with using photoluminescence on this, where you see the pristine, and using graphene or graphite as a substrate, what happens. Our goal was completely different. What we wanted to do is, we wanted to look at whether our optoelectronic functionality can lead to some way allow us to estimate the binding energy. All we have found is the binding energy that we estimate from the optoelectronic functionalities like this is consistent with that obtained from the photoluminescence measurements. However, our method is not accurate to say whether having the graphene nearby is going to change the binding energy too much. There is some reduction which is expected because of the screening, but we are not accurate enough to make a comment on that.
Yeah, the last, just a clarification here. So here in this slide itself, so when you have the electron got transferred very fast, and still you see a photoluminescence, good enough photoluminescence, means electron.
Oh, no, you're absolutely right. Photoluminescence strongly quenches. Okay. So I did not show that data, unfortunately, but it's there somewhere, but I didn't want to go to that detail. But yeah, you're right. The moment you have got graphene there, the photoluminescence quenches, boom, straight away. And as a matter of fact, it recovers a little bit. This is the question from Ashish, which I was trying to answer. And we have the data in this paper itself. That data is there as a function of temperature. So we looked at the photoluminescence as a function of temperature, and we found that the photoluminescence slowly starts recovering at lower temperature, where the excitonic recombination time scale becomes smaller, and hence there is a competition between the charge transfer time and excitonic recombination time becomes comparable. That's when you start seeing a slight recovery of the photoluminescence.
Okay.
But at room temperature, boom, all flat, no photoluminescence.
Okay, maybe I said last, but this is not a question, rather your comment. Say, do you see a problem when you go to a longer wavelength, like infrared, etc.? Do you have enough material of this kind quality to have a good photo detection?
Not the chalcogenides, unfortunately. Black phosphorus, people have done lots of black phosphorus graphene infrastructure. The black phosphorus has got a little lower band gap. So this is one of the key goals of this field now, to see how we can sensitize this to infrared or even lower wavelengths. So what I showed you today is pure photoconductive. What I did not show you, because that work is going on, is using volumetry. In principle, we should be able to go to much longer wavelengths, because we will start using heat as for our observable. But that's going to come up later.
Okay, thanks a lot. Thanks a lot once again. Yeah.
Thank you, Amsuran.
Arindam, thanks for this wonderful talk. I
Thank
learned
you.
a lot. So I'm not from this devices field, of course, but I have certain questions. One is, what temperature are your experiments carried at?
We calculate, we do these experiments now with the temperature of room temperature to 10 Kelvin or so. Most of this work has been done at 80 to 100 Kelvin, but we have exactly the same structure at room temperature.
I see. So, I mean, when you reduce the temperature, when you go to liquid helium temperature, the responsivity, photoresponsivity increases or decreases?
Well, I mean, that's a good question. It's not something very clear. See, the problem with very low temperature is that you start playing around with time scales, right? Because then the recombination time scales become very different from the room temperature. And many of the electrons actually come back, instead of going to graphene, they rather decide to recombine. And the point that you just said is exactly what happens at very low temperature. So we do not see a very large improvement or increase in the responsivity at low temperatures. But I think the best region of responsivity per se is in the order of 40, 50 Kelvin to about 200 Kelvin range. After that, what happens is the phonons become really active. And they immediately, as soon as the electrons get transferred, the phonons start transferring it back into chalcogen layer. And again, the responsivity starts coming. Okay. So there's an optimal temperature range that is important.
Thanks. And to begin with, your chalcogen layer, is it also doped, or what's the doping state?
We have done both. See, the chalcogen layers are not doped intentionally. They come. So the MOS2 usually comes with a very strong N doping by itself. But there are this tungsten disulfide, diselenide, etc., which are relatively undoped. We find better results with the undoped ones, for example, the tungsten disulfide or diselenide. But overall behavior is the same.
I see. Okay. And one last question. So you showed this plot where you have like the status, the state of the art of where these devices lie and where the various materials lie. Can you kindly tell where would gallium arsenide and silicon based devices lie on that?
Silicon is one. So I'll tell you where. Okay, so I had it in a different plot, but I can indicate it on this itself. Sorry.
Yeah.
I think I have it here. No. Okay, silicon is here. You can see my pointer?
Yes.
Silicon is in this order.
Okay. Okay. Towards the right side, or?
Well, I mean, the bandwidth of silicon, it depends upon the device. So it's very fast. So you can make, well, I mean, single photon detection is difficult, but overall it will be somewhere here.
Okay, I see. I see. So this is a great improvement with graphene-based hybrids, at least in terms of responsivity.
Responsivity, there is no competition right now.
Yeah.
The question is how to make it fast.
Right. What about gallium arsenide-based things?
That's very similar. Actually, what people use as avalanche photodiodes are silicon or aluminum indium arsenide, or gallium antimonide, and these kind of semiconductors. They are all in the. I mean, I'm talking about these systems which really have been pushed into the single photon detection. And there, we are limited by an overall bandwidth of about 100 kilohertz or something of that sort. One of the main reasons why people have gone to superconducting single photon detections now, because that is where the detection is happening at, because the thermalization time scale in those is in the order of a few tens of picoseconds, which means you can in principle go to a bandwidth in the order of few megahertz or up to few maybe tens of megahertz or so. Key bottleneck in quantum technology itself, and maybe graphene can solve it.
Thanks. So I will stop and let students ask things.
Sure.
Hello.
Yeah.
Yeah, sir, I had a very basic doubt that you explained the theory using the quantum dot, right? Like here, graphene is doing that thing that it's capturing the electron. So, like in lab, how do you realize that quantum dot, and why not using that instead of graphene?
Right. So I think the question that you asked was when I showed the quantum dot hybrid structure that just show me, tell me this is the right one or not. It's not too far. Give me a minute. It can go there. This one, I guess. Sorry. Is this the one that you talked about? This is the only quantum, right?
Yeah. When you told the theory of like electron get capturing about.
Correct. So this was what I was trying to tell you. So here this is the graphene layer already. See, graphene layer is the common transport layer in all these hybrid photodetection structure or this kind of structure. So you have to have a graphene layer no matter what. So you can see, even if you zoom out this picture, have a look at this Nature Nanotech paper from Constantos. The basic structure is there is a layer of graphene already. What you do is that you put a layer of quantum dots on top. Why do you need a quantum dot? Is exactly why we use molybdenum disulfide later. See, the quantum dot is a light absorbing material. So what happens when light comes, the quantum dot captures that photon and electron hole pairs are generated within the quantum dot. And then what happens once the electron hole pairs are generated, exactly the same reason, in this case hole, because of the band alignment is such that the hole finds it easier to jump out of the quantum dot and go into graphene. And then the rest of it is similar. That is, the hole goes back and forth many times. And at some point of time after that, the hole essentially gets recombined with this electron. So you always need the graphene layer. Graphene, it is not about using quantum dot instead of the graphene. It's graphene there, but you need a light absorbing layer, and the whole quantum dot is acting as the light absorbing layer. Does it make any clearer?
Yeah.
Hello, sir. Yeah, I have one question in the same line. So, in this particular case, what is the transit time? Like, is the transit time?
That's a great question as well. Yeah. So the transit. So this is why it's so important to. If I go to this. So typically, here you can see the number is given. So typically, it takes about a second or so for the holes to jump out. Electrons. This is something which is also very inaccurate. Actually, if you have the electric field, it can go to hundreds of seconds without electrons coming back in here. So that's the lifetime of the electron hole pair. Remember, which is actually, and this tau transport is the transit time of electrons along the graphene layer. It goes between here to here. And given the kind of mobility that you have in these systems, the transit time can be about a nanosecond or a little less than a nanosecond.
Okay, sir. Good. Thank you.
I have one question.
Sure.
So I guess whatever you have discussed over here are all exfoliated monolayers or multi-layers. So I wanted to know what change can we, or what else can we expect if we use CVD grown TMDs like CVD grown graphene to make hybrids?
Great, right. You are absolutely right, and it's a very good question. So first of all, now even CVD grown systems hybrids are being generated at the wafer scale of such structures. Now, what change can you expect? Obviously, first thing is the mobility. That said, though, there are now mobility of the graphene layer, which is CVD grown, can be as high as exfoliated these days. About 20,000, 30,000 mobility is not very uncommon. So if mobility goes down, then the transport time becomes longer, and hence gain can be smaller. That's number one. The second thing, which I think is more important, is the chalcogen layer quality with in the CVD grown systems. Grain boundaries that could lead to trapping of carriers. So there are various other possibilities. However, we have done experiment with exfoliated MOS2 but CVD grown graphene heterostructure, in which we found the performance is almost identical. So it's very little difference. But what happens with the chalcogenite, which is CVD grown, is something which is not very clear to me. But I'm guessing it will lead to a significant reduction in the responsivity, although how much, that I don't know.
Okay.
Hello, am I audible, sir?
Yeah.
So just one case, you told usually the dark current is very high for this even MOS2 in microamperes.
Can you, yeah, dark current is in microampere. Just speak a little louder.
Oh, sorry. Am I more audible now?
That's okay. I can hear you. Go ahead.
Okay. No, I'm speaking via Bluetooth. I'll turn that off. It should fix. Sorry. So now it's fine.
Yeah. Now it's perfect. Perfect.
So the question is like, we do grow CVD, means TMD is using CVD. And sometimes for WS to WSC2, I typically get very low dark current. Dark current at 1 volt bias is in the order of few picoamperes.
Correct.
So my question is, now if I do expect when the system is defective, it will be more conductive. So can I say that since dark current is low, it might be more defect free? Is there a likely chance?
Right. So let me just separate out your question. So first of all, what you see in your chalcogenide based system, the dark current is low. You're absolutely correct. But that current is the current through the chalcogen layer, correct? So that is determining your dark current. Whereas if you look at the devices here, the dark current is determined by that resistance of graphene, which is orders of magnitude smaller than the resistance of the chalcogen layer. So if you want to look at the photo response of an individual chalcogen layer, for example, WS2 or MOS2 or whatever it is, there your dark current is limited by the conductivity of the chalcogen layer. So as a result, if you have got defective chalcogen layer, your dark current will be smaller because the resistivity will be much larger, but that will definitely degrade your photo response as well, because there would be a lot of recombination within the chalcogen layer. Whereas in this case, one of the big advantage of this case, although advantage or disadvantage depends upon your point of view, is that the dark current is limited by the graphene, and the addition of charge and taking away from charge is happening because of the TMDC. So the TMDC is not playing any role in determining the dark current.
Yes, no, I just wanted to know, can we use not regarding this device, rather can you use dark current to say how good the sample is of the teas?
Okay. In principle, yes, you can say, because if the quality of the device is not very good, then the current through the device will be small. So you can actually say that, yeah, go ahead.
No, this is regarding your device. Sorry, I just think I didn't make it very clear then. So in your device,
in my device, I lost you. Can you hear me, or I can't hear you?
I think he's disconnected or something.
Oh, okay. You can hear.
Audible, sir.
Yeah, you are audible now, but you went silent for a minute, for a few seconds. Can you, I think, yeah.
Gokul, I think your network is poor. Can you move to other place?
Yeah, that would be helpful.
Gokul, you are not audible.
Hello, I'm audible.
Yeah, I can hear you now.
Okay. Okay. No,
Try
sir.
again.
Like, is the electric field that is stopping the. Am I audible?
Yeah,
So sorry for
Go
the
ahead.
connection.
Yeah, go ahead.
So it's the electric field within your graphene layer that is preventing the electron from jumping back to MOS2. Am I right, sir?
Correct. That's right.
Okay. So
You're right. That is correct.
let's say you right now without. Okay, if you stop, it can go back to the normal state, right?
If you change the voltage,
let's say you pulse-
then it becomes, then it is possible for the electron to jump back into TMC.
Okay, so like let's say I made the potential difference to 0. I pulsed it, it was going. Rather than putting a gate pulse, I simply stop applying the voltage, then I reapply the voltage.
Absolutely,
Okay.
absolutely. So that's how we reset the device.
Oh, okay, sir. Thanks a lot, sir.
Yeah.
So I have one small question in this slide. So here the photocurrent versus wavelength scan that you are showing is for this graphene WAC2 hybrid, I guess. So I want to ask what change in the peak features do you see if you just measure this on WAC2 layer, maybe multi-mono, whatever?
Sorry, say again. What do you see?
These peak features, this BAA minus, do you see any change when you just measure only on WAC2 instead of this hybrid?
No. So they are okay. So this was done not on the, so the way we did this experiment is that we have got graphene WAC2. The part of WAC2 which was extending out of the graphene region, we see that it's the same layer. So in the overlap region, all these are quenched heavily, the photoluminescence, So we have the part which is away from graphene, we look at that region and we get the information on the optical states. So this is the photoluminescence of the region which is away from the graphene region.
Okay.
Anybody has any other question? Okay, good. I think there's no more question, right?
So I think there is no question. So thank you, Professor Ghosh, for this wonderful talk.
Thank you, and stay safe. Okay, then we can log out. Thank you, guys.
Yeah, we can conclude if no one has any other question. Thank you, Professor Ghosh.
Thank you. Bye bye.